All right, hello everybody. So we are going to be working on exploration 1 and 2 for day 16 of the geometry notes. So you can see my screen, you'll see I am in GeoGebra, the link that I put on the notes. So exploration 1 is asking us, so we use GeoGebra to draw segment AB with endpoints 0, 0, and 6, 0. So what we're going to do is we're going to click over here. We're going to put point, and we know that we're going to have a point in 0, 0 right there, and then in 6, 0 all the way over here. So we have those two endpoints. Step B, they're asking us to draw the vertical line x is equal to 3. So what I'm going to do is I'm going to click here on input, and I'm going to do x is equal to 3. And as you can see, we have a vertical line right there. Step C says draw a triangle ABC. So C is on the line x is equal to 3. So we're going to put a point C somewhere on this line, somewhere on this line. So it has to be, it doesn't have to be a specific number. In fact, I'm just going to put it anywhere right there, let's say, and let's ignore this for now. For now, we're going to be calling this point 3 and y. So in other words, this is our point A, this is our point B, and this is our point 3y. And so if we want to create a triangle, we're going to click on this triangle here. We're going to click on polygon. And all we have to do now is click on each vertex. So we click on each vertex all the way around. And as we can see, we have a triangle right here. So once we have our triangle, they're asking us, use the drawing. So we have to use this triangle here to prove that triangle ABC is an isosceles triangle. So if we have an isosceles triangle, we're gonna have to get two equal sides. And over here, we can kind of cheat a little bit and look at our measurements here. Look, B and A both do have the same measurement. But again, let's assume we do not know that. And if we assume we do not know that, then we are going to have the following. So let me just switch over to my document camera. So there we go. So I'm on my document camera. And so the triangle that we drew in GeoGebra, again, it's gonna look roughly like this, right? We have a triangle. We have something like this. This is our point 0, 0. This is our point 6, 0. And this right here, like I said, we have to name it that point 3 and y. And so what we have to do is we have to use this drawing here to prove that triangle ABC is an isosceles triangle. In other words, we want to show that this side and this side have to be congruent. So how do we know whether two sides are congruent? Well, they need to have the same measurement, right? So if we are looking for the same measurement, we can actually find, and let me call these points. This one was A, this one was B, and this one was C. And so if we want an isosceles triangle, we need segment AC, the measurement of segment AC, we need that to be equal to the measurement of BC. And so how do we find that? Well, we have to use our distance formula. So if you don't remember the distance formula, it's this one right here. All right, so remember, if we have 2 points, we can find the distance between them if we use this formula right here. So I'm going to put this right here on the side. And so really all we have to figure out now is the distance between AC and BC. So the AC is actually the square root of, and now we have x2 x2 minus x1. So 0 minus 3. 0 minus 3 to the second power plus, and then now we have y2 minus y1. So that's going to be 0 minus y to the second power. And then we're taking the square root of this. So if we simplify, we're going to get that. This is the square root of negative 3 to the second power plus negative y to the second power. And then using some algebra, we now know that negative 3 to the second power is actually a positive 9. And the negative y to the second power is actually a positive y to the second power. So this right here is the distance of the segment AC. And now let's see what the distance of the segment BC is. If it ends up being the same, then we have our isosceles triangle and we will have solved this problem. So let's see. BC is going to be, again, the square root of, and we need to find the distance between these 2 points. So we have x2 minus x1. So that's 6 minus 3 to the second power. That's a 6. And then plus y2 minus y1. So that's going to be 0 minus y to the second power. And then again, we're going to use algebra to solve. 6 minus 3 is 3. 0 minus y is just minus y to the second power. 3 to the second power is just 9. Negative y to the second power is y to the second power. So now we are done with our process. And if you notice, the distance of AC, which is this right here, and the distance of BC, which is this right here, are actually the exact same thing. So the triangle is isosceles. And we are done with exploration 1. All right. Now, exploration 2 is dealing with something very, very similar. Right, so we're going to be using the same tools, but now we're going to build a slightly different triangle. So let's see what triangle we're going to build this time around. So we have exploration 2. All right, and so I'm going to switch back into GeoGebra, which is this right here. And let me refresh so that everything gets cleaned. And once again, let's follow the same exact steps, but now for exploration 2. So exploration 2 tells us the following. So use GeoGebra to draw segment AB with endpoints 0, 0, and 6, 0. So the beginning part of this exploration 2 is actually the same as the other one. We're going to mark 0, 0. And we're going to mark 6, 0 right there. And then step B says draw the vertical line x is equal to 3. So just like before, we're going to draw x equals 3. And that's our vertical line right there. And then step C is where it changes, right? It says then plot the point C, which is 3 and 3. So now we have to find points 3 and 3, which is 3 and 3 right there somewhere. So there's our point 3, 3. And now we have to draw a triangle. So once again, we're going to click on our polygon tool. We're going to click on each of the vertices to create this triangle right there. So now we have to use this drawing to prove that triangle ABC is an isosceles right triangle. So once again, I will draw the triangle that we have there, a very quick version, a sketch. Looks like this. It'll look like this. This is A, 0, 0. This is B, 6, 0. And then this one right there, we said was 3 and 3. All right, so this and what I have in the image are exactly the same. And so now we have to use our drawing to prove that triangle ABC is an isosceles right triangle. So we have to prove two things. We have to prove that this segment and this segment have the same length. And then we also have to prove that those two segments are perpendicular so that we get a right triangle right there. So let's see, let me switch over to my paper and let's see how we're going to be able to do this just using algebra. All right, so we have, as you can see my drawing here, once again, I want to figure out what the length of AC and BC is so that I can compare them and check if they do have the same length. So let's see. So once again, we're going to use the distance formula. I'll put it up here again, this distance formula. Right there. Which tells me that if I want to find the distance of A and C, all I have to do is take the square root. Let me zoom in a little more. Right there. So take the square root of x2 minus x1. So that's 0 minus 3 to the second power plus y2 minus y1. So another 0 minus 3 squared. If we simplify, we're going to get that. This is negative 3 to the second power plus another negative 3 to the second power. Now, negative 3 to the second power is 9. So this is actually the square root of 9 plus 9, which is actually the square root of 18. And if we simplify this, this is going to turn into a 3 times the square root of 2. So we have to find the same exact process for BC and hope that we get 3 square root of 2. So let's see what happens. We're going to have BC. Once again, we're going to use distance formula. X2 minus X1. So that's 6 minus 3 to the second power plus Y2 minus Y1. So 0 minus 3 to the second power. And if I simplify this, I'm going to get positive 3 to the second power plus a negative 3 to the second power. But once again, both of these things are actually positive 9. So we're going to get square root of 18, which again is just 3 square root of 2. So because BC and AC have the same exact measurement, we know that these two things should be congruent. So now that we figure out that this triangle is isosceles, we have to figure out how to get this right triangle. And so if we remember from our definition of slopes, here's how I find my slope. Sorry, no. Here's how I find my slope. Right? If we have 2 points, we can use this formula to find my slope. So let's see what happens. Let's find the slope between A and C. So I'm going to scoot my paper over. Put this on top. And so now we're gonna see if we can find the slope. So I'm gonna call it M, the slope of AB. And we have slope of AB. And that's going to be, sorry, AC. I should call it AC. So AC is going to be Y2 minus Y1. So 3 minus 0 over another 3 minus 0. So this is actually 3 over 3, which is equal to a positive 1. Let's see what my other slope tells me. If I find the slope of segment BC, let's see what we get. So once again, Y2 minus Y1 is 0 minus 3. And then X2 minus x1 is 6 minus 3. So then we're going to have, oh, this is going to be minus actually. So we have 0 minus 3 divided by 6 minus 3. Yep. So we're going to get that this is a negative 3 over 3, which is actually a minus 1. And so if we remember, the definition of perpendicular slopes are that if I have two slopes, if I multiply these two together and I get a negative 1, that means that my segments are perpendicular. And so if we notice, we can take this slope and multiply it by this slope. In other words, the slope of AC multiplied by the slope of BC is going to be 1 times a negative 1, which is negative 1. Because this multiplication is negative 1, so we can say that segment AC is perpendicular to segment BC. And we are done. We proved that these two segments are the same. So this is an isosceles triangle. And then we also proved that those two same segments are perpendicular, which means that there is a right angle right there.